Good night, everyone. I'm really happy to be here. I'm really happy to see a lot of people. And today we'll talk about distributed systems, distributed databases, and also about single node databases. We'll talk about the spectrum between being an ACID database and being a base database. So let me introduce myself. I'm Renan. I come from Brazil. This is CloudWalk, the company that I work at. This was a Rust meetup that we did last month. So it was the biggest meetup for Rust in Brazil. I'm pretty happy with this. A lot of people show up, about 50 people show up. And that's great. We are making a community grow there as well. And going back to the topic here, I will discuss a bit about NoSQL and the context that it had on data. I'll also talk about ACID and base, what it is, why it's necessary for everyone to know about it. I also show some use case of people that didn't know enough about base and made some grave mistakes. And I will also show and share a bit of code patterns that I do because I'm migrating a lot of applications to Rust right nowadays. And I will share some code patterns that are useful for everyone in here. So let's begin taking a trip down the memory lane and begin like 15 years ago, whenever we went to a conference, whenever we went to a meetup, people were saying like SQL is dead, NoSQL is the future, NoSQL will have the same impact as Ruby on Rails had on frameworks. So everything will be NoSQL. And what's NoSQL? What was people so hyped about back then? So NoSQL is a broad term for everything that's not the relational database. And what's a relational database? Is anything that has ACID guarantees and also have relation between tables. And now let's talk about ACID. Let's begin with some definitions here so we can understand better the problems that we are solving. So ACID stands for atomicity, which is your transaction work as a whole unit. So you have a bunch of changes going on under a transaction. However, atomicity makes sure that either all transactions get all the changes get committed or no change gets committed whatsoever. So it's an all or nothing choice to make. And another property from ACID is consistency, which is a lot of validations from your data. So if your data is valid, it is consistent and it will get committed. If it's not consistent, it won't get committed. Isolation allows you to separate transactions and don't allow you to have two transactions being committed at the same time. So isolation is what avoids racing condition from happening and data from being overwritten, like in an injection or in attack. Durability means your data will be saved on several mechanisms, such as the write-ahead log from Postgres, or it will be a backup, or it will be a replica. There are many ways to have durability. However, write-ahead log from Postgres, I think, is the most notorious one. So isolation is closely related to serializability. And serializability basically means your data will be written in a serial manner on the database. So now talking about the pH scale that we are seeing here between ACID and base, let's go to the base side. So base is a broad term that a few researchers came up with, and I think it's a wordplay between ACID and base. And it's to show that it's not a binary choice. It's more of a spectrum. As we will see further down, not all databases like Postgres says it's ACID, but it's not purely ACID. It had to make some decisions to be not so ACID and to go towards the base side. Otherwise, the performance would be just awful. It would be not practical. So base stands for basically available, soft state, and eventual consistency. Basically available means your data will always be available for both read and write. So a pure base system is always available, regardless of the circumstances of the network, regardless if a machine crashed, everything should be able to receive a transaction and answer a query. Soft state means when you are dealing with different nodes on a distributed system, you won't have the same state everywhere. You need time for replication to happen. You need time for consistency to fit in. And that's the eventual consistency part as well. So data will eventually go to every node that's calling for it. So let's look at a real use case of Bayes. So this is YouTube. I think this is an old bug that they had. It was showing for me that there are many more likes than views, which doesn't make sense because you need to watch the video in order to like it. So this is eventual consistency. The views that are showing up here are not the real views, but it's the views that they choose to show in order to display the video, because nobody will die if you show the wrong number of views. But people want to watch the video as soon as possible. They don't want to wait you to calculate things to show the correct number of views. So basically this choice to performance, to prioritize performance and scalability. And this is a cool study from Brown University. They have this database, they created this database called HStore. It's not to be confused with HStore from Postgres. This is an entirely different thing. This is a in-memory database that was designed to be really, really fast, to have a real high throughput. And they were studying, like, okay, why are we so slow? And they came up with this calculation here. So a lot of the time being spent on writing transactions was just granting the isolation part, the durability part, the atomicity part, all the acid parts were taking a lot of time in order to get the transaction committed. And there's the optimal part here, down here, which is the actual data being written. So they figure like Bayes is basically forfeiting consistency and isolation in order to have greater availability and performance. And of course, there are some business that greatly benefits from having great availability. However, there are other businesses such as banks or medical systems that cannot afford to lose the consistency or the isolation. And here I want to show a case that happened like 10 years ago. So there was a crypto exchange that got bankrupt because they didn't know enough about isolation. And they lost what's now $65 million. However, this value was much lower like 10 years ago. However, it was enough to bankrupt them. So how was this attack done? Basically, what I'm showing here is two transactions running concurrently. On your left, there is the moment of the transactions. And this is an oversimplified case. Of course, I don't have access to the whole source file from them. However, this is what happened according to all the reports from the data engineers that look at it. So on T1 and T2, the first transaction begins, and T3, T4, the second transaction begins. Notice that on T2 and T4, there is the set transaction isolation level to read committed. However, this is the default isolation level of Postgres. This line is not necessary. If you run any transaction on Postgres, this is the isolation level that they will have. And on T5, you have an update balance withdrawing 10 Bitcoins. But on T6, on the concurrent transaction, you have another update of balance adding 1 Bitcoin. And what happens on T7? You commit the first transaction, you unblock the second transaction, and the second transaction, when you look at the balance is 11. And when it gets committed, the actual balance from the attacker went up instead of down. So he withdrew 10 Bitcoins and got 1 Bitcoin back into his balance. If they knew about raising the isolation level on Postgres by setting the state to at least a repeatable read, they could prevent this problem. Because when repeatable read runs and it sees that there is another concurrent transaction updating the same place, the same value, it tells you, you cannot do this. You only will be able to run the first transaction. So if they knew this simple thing here, they would be able to survive and they would probably not bankrupt anytime soon. So this here is a list of the databases and the default isolation level that they have. And notice, acid is a spectrum. So not a single database comes fully acid. They all have intermediary value because they are prioritizing a bit of speed. And you can strategically, and you can choose where you want to raise the isolation level, because you can do it inside of a transaction. You don't need to set the isolation level for the whole thing. And the highest isolation level is serializable for both Postgres and MySQL and MariaDB as well. However, for Oracle, even if at the highest isolation level, it's still susceptible to 2 vulnerabilities. And those vulnerabilities come from Janus testing framework. It's a framework for testing vulnerabilities on database, possible injections. And the best databases that I know make tests there. And let's talk about code. Let's talk about some real world things. I will share some code using Postgres. But just before I share some code with Postgres, I want to reinforce this point that the ACID spectrum can be movable. So Postgres by default comes closer to ACID and farther from base. However, if you use a serializable isolation level, it becomes much more acidic. If you are using many replicas at the same time and you haven't configured synchronous standby names, it will become a lot more base, because only the master transaction will be committed, and if you try to read from a replica, the data will not be there. The data will eventually be there. So eventual consistency is a base characteristic. And I always see people making the same mistake of querying a database that has eventual consistency and getting frustrated because the data is not there. So this mistake happens because people don't understand about the ACID and base trade-off. And if you set synchronous commit as remote apply, Postgres will become much slower. However, every node that it has will be aware of all the changes that you committed. So this is talking about Postgres. However, if you work with Scylla, Cassandra, or any other database that I know, any major database nowadays have this sort of configuration. You can use even Cassandra, that's database clearly designed to be NoSQL. For some reason, if you want to make it acidic, you can use things such as lightweight transactions and force the replication to be on all of them. I don't know why would you do this, because Cassandra will be really slow if you do this. However, it's possible. And I want to share some patterns, some code patterns that I use on Rust. Mainly we have a lot of legacy code in Ruby, in JavaScript, in Python, and we are rewriting everything in Rust for the great reliability, great speed that it has. And one pattern that I always adopt is using multiple pools. One for the primary. We don't use multi-master structure on Postgres. I don't recommend it at all, but some people use it. We use only a primary node for writing, and sometimes we use multiple replicas. But in this case, it's for only one replica. And what we do is create a pretty much average initializer, and then we create 2 functions. One, to make sure we always read from replica, and be aware, many of our databases have eventual consistency, so people need to adapt the system to read the replica when the data is actually there. And we also have a function to write the primary. So this enforces that. One problem that we run very often on my company is the amount of I/O operations that are happening. And how do you prevent a lot of I/O operations? You distribute systems, so you adopt base characteristics. And this is what we are doing here. We are throwing a lot of the reads through the replica, so the I/O gets spread throughout many replicas, and the write goes through a single place. Another thing that is useful is strategically choosing where do you want to use isolation. So a lot of our transactions are like update the address from the user, update the name of the user. Not the name, it doesn't make sense to change your name, but we update a lot of data for the user that are not critical, does not need a high isolation level. However, if we are dealing with his balance, or if we are dealing with money transfer, we always set the isolation level to the proper one. And this is another pattern of doing round robin for replicas. So if you have multiple replicas, you can use an atomic queue size and just increment it when you are reading. And eventually, every replica will get the same share of requests. This is really useful if you are having a lot of I/O going on. And this is pretty much it. I could share more examples, but if you want, you can ask or we can talk later. Overall, just to conclude and get back to all the points that we have here, ACID is not always purely ACID. So you have a spectrum, and all the databases ship in the middle of the spectrum. Of course, they will be leaning towards one or another. However, not everything is purely ACID. Be aware of it. Consistency and availability, they are different things. You need to choose one. There is this CAP theorem. It's very talked upon on the Designing Data-Intensive Applications book. It's a really nice book. I recommend everyone in here to read. And basically, you have to make a choice. You are either prioritizing availability or you are prioritizing consistency. If you make an accidental choice, bankruptcy can happen. And also, there are a lot of testing tools for infrastructure, such as Litmus Chaos. This one I used many times. It's great on Kubernetes. That's Gremlin. That's Chaos Mesh. There are many tools. There is the Janus framework itself. So use those tools in order to know what vulnerabilities are you susceptible. This is the books that I used to prepare this presentation overall. The DDIA is really important. I really recommend you all to read this book. Also, the Postgres internals is really nice if you want to know about what's going on under the hood on Postgres. This is the reference, and thank you all very much for listening to me. Should I hold your alcohol or what?
No, never. No chance. Thank you for the talk. If you wanted to build your own database for a blockchain of the ACID base, 8 properties or other properties, what would be the unique property that you would focus on to make your blockchain go faster?
Yeah, it's awesome because we created a blockchain, and this will be my talk on Friday. And I spent a lot of time thinking, okay, what did I choose for Stratus, which is the blockchain that we created? And for Stratus, we choose to go to the ACID side because we are dealing with a lot of money and we don't want to lose people money. So we choose for consistency. We could make some choices towards a more base design. However, we were like, okay, we will have only one miner on our case for Stratus. We will only have one instance, and the other instance will be only replicas, and they will have eventual consistency, or they will be synchronized eventually. But the main miner, it will do all the things on the most acidic way. However, if you look at the broad blockchain scenario like Ethereum or other blockchains, I think they have, of course, they have consistency. However, it's an eventual consistency. If you commit something right now, if you throw something on the blockchain, it will take a while to get to other nodes. So it's a very interesting distributed system scenario. And also, one thing that blockchains are notorious for suffering is the speed. So due to this distributed nature, and also trying to keep the consistency on the distributed nature, I think they suffer for a lot of speed. Yeah, that's true. Yeah, 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 yeah. In my case, I just use RocksDB and throw the problem to Facebook guys. I say, okay, Meta guys, solve this problem to me. So to be honest, the indexing part is the part that gave us a lot of speed. So Stratus is really fast because we use the RocksDB indexing technology. And of course, we did our fair share of efforts, like in my case, personally, and I will get to an interesting point here. The indexing of Stratus uses Bean code, which serializes the data structure using the same mechanics of Sergi. And if you look at other databases such as Substrate, it uses Patricia Merkle tree. And Patricia Merkle tree will create a tree, will do a lot of hashing, and this is the indexing process for them. This is much slower than just writing to a key value. However, I think there is there are some other things down the road. I need to find out what's faster than RocksDB. If someone knows, I think in memory is very promising. We have some people wanting to try it, and I think it's a very nice question. Thank you.